Now let's talk about the classical method that was used to conclude a hypothesis test, which was the rejection region or the critical values method. So rejection region or critical values will always give you the same result as p-value. It's just critical values. You can do both tests, z and t-test, using either p-values or critical values. Typically what's going to happen is p-values are going to be easier for a z-test, and critical values are going to be easier for a t-test. But you've got to be comfortable doing both. You're going to see both on the final. Alright, so the way the rejection region or the critical region works is you find the range of values for which the null hypothesis is not probable, and then you calculate your test statistic, and if your test statistic falls into that region, the null hypothesis is rejected. So basically that critical value z naught separates the rejection region from the non-rejection region. You might also see this called zc. And essentially the way you get this critical value of z is based on your alpha level. So it still goes back to alpha, and essentially we're doing it kind of backwards to what we did before. So before we would get a p-value, compare p-value to alpha. The way critical regions works is we use that alpha, we get a z value, and then we compare that critical value of z with our test statistic. So instead of converting the test statistic to a probability, we're going to convert our other probability alpha to a statistic, to a critical value. So most of the steps are still going to be the same. So you're still going to specify your level of significance alpha, figure out if you're doing a left-tailed, right-tailed, or two-tailed test. The difference comes now in finding your critical values. So to find your critical value, z naught, then basically what you want to do is if it's a left-tailed test, you find the z-score that corresponds to alpha. If it's a right-tailed test, you find the z-score that corresponds to an area of 1 minus alpha. And if it's a two-tailed test, you find the z-score that corresponds to 1/2 alpha and 1 minus 1/2 alpha. But that sounds like a lot of words. It sounds really complicated. It's not. Essentially what you want to use is go back to that last page in your course pack and use table 3C. So what that table looks like is this. So literally it tells you, so if your alpha is 0.05 and you're doing a left-tailed test, there's your critical value. If your alpha is 0.05, you're doing a right-tailed test, there's your critical value. And if you're doing an alpha and you're doing a two-tailed test, there are your two critical values. Same thing for alpha equaling 0.01. So all you do is you look on this table and you find it. So let's say we want to find the critical value in the rejection region for a two-tailed test with alpha equaling 0.05. So alpha equaling 0.05, two-tailed test. So we go back to this table. There's alpha equaling 0.05, so we care about that column. Two-tailed test, plus or minus 1.96. So in this case we know that our critical value z naught is equal to plus or minus 1.96. So then what does this look like? So we sketch out our region. So our z distribution. So here's negative 1.96. So that's z0, negative z0, the negative value of z. And then our positive value, so z equaling 1.96. And so then everything that lies in the tail, so everything further out away from those test statistics, that is your rejection region. I'm going to abbreviate that as RR. So, and then everything in the middle, in between those two tails, is your do not reject region or fail to reject region. And so then all we do if we're going to conclude the test is you look at where your test statistic lies in relationship to the sketch. So you just add your test statistic to it. And so if your test statistic lies in one of the two rejection regions in this case, then you would reject the null hypothesis. If your test statistic lies in the do not reject region or the fail to reject region, then you would fail to reject the null hypothesis. All right, so let's go back and look at the test that we did earlier using p-values. So our auto racing example where the pit crew claimed that the mean pit stop time is less than 13 seconds, and a random selection of 32 pit stops had the sample mean of 12.9 seconds, assuming the population standard deviation is 0.19 seconds. And we still want to know, is there enough evidence to support the claim at alpha equaling 0.01? But now we're going to solve this using critical regions. So now the only difference, so alpha equals 0.01, and we know we did a left-tailed test. So by critical regions, to get our critical value, so Z naught, all we do is we go to that table and we look up our value of alpha equaling 0.01. And for a left tail, we know that their critical value is going to be negative 2.33. So Z naught is negative 2.33. So then we sketch out our region. So if this is our Z distribution, Z naught is negative 2.33. So everything that lies to the left of Z naught is our rejection region. Everything to the right of Z naught is our do not reject region, or our fail to reject region. So then all we do to conclude this test is we look at that test statistic, and in this case we've already calculated it, negative 2.98, and we just put that on the graph where it's supposed to be. So negative 2.98 is somewhere right in here. So because our test statistic Z equaling negative 2.98 lies in the rejection region, our conclusion is that we reject the null hypothesis. And notice that is the exact same conclusion that we came up with when we did it by p-values. So let's look at the other example we did. So we looked at the mean cost of bariatric surgery, and according to the study, they've said it was $21,500. You think it's incorrect. So you got 25 bariatric surgery patients, found that the average cost of their surgeries was $20,695. Population standard deviation was 2250, and it was normally distributed. And so we want to know, is there enough evidence to support your claim at alpha equaling 0.05? So alpha equals 0.05, and we did a two-tailed test. So we go back to that table, alpha equals 0.05, go down to a two-tailed test, and you get plus or minus 1.96. So Z naught is plus or minus 1.96. So same idea, sketch out your Z distribution, put your test statistics on here. So negative Z naught equals negative 1.96. Positive Z naught equals positive 1.96. Area in the tails are our rejection regions. And area in the middle is our do not reject or fail to reject region. So then we go back and we compare our test statistics. So in this case, we got negative 1.79 for Z. So negative 1.79. When we plot it on here, it's somewhere about right here. And in this case, because that test statistic lies in the do not reject region, we're going to fail to reject the null hypothesis, which is the same conclusion we came up with by using p-values. And again, you should always get the same conclusion whether you're using p-values or critical values to test using the Z test. Now, with the t distribution, if you're able to calculate the exact p-value, and we'll talk about that, then you should always get the same result as well. The issue is going to be with calculating the exact p-value based on the way our table is set up. Now, it's also worth mentioning your book does have another critical values table you can use. I only mention it because you might need to find a value for a different alpha value based on the type of test you're doing. So then the way that table's set up, remember, so you still know your level of confidence, alpha, but the table's going to give you z alpha over 2, so it's only going to give you half of that. So if you're doing a two-tailed test, fine. This table is going to give you two-tailed values easily. If you're doing the one-tailed test, you just got to remember to actually half your alpha to get the right z critical value of z. But in general, so this table is nice because it gives you more values. The issue is it's harder to use. So for the most part, I'm going to expect you to use the other table, table 3C, to find your critical values. But you might see it on the homework where you need a critical value of z for a different alpha level, and that'd be the only case you would need to use the other table. On the final exam, you're only going to, for critical values, you're only going to have alpha equals 0.05 or alpha equals 0.01. All right, so now for t-distributions. So I'm going to talk about in this video how to find critical values for t-distributions and how to do the t-test for the sample mean or for the population mean. And then there's going to be another video on Moodle to show you how to do the p-values for a t-test, just because it's a little more in-depth. All right, so same idea. So the only big difference is going to be, keeping in mind, since we're doing a t-distribution, we need degree of freedom. So degree of freedom is still going to equal to n-1, just like it did in Chapter 8. And so then basically what we're going to do to find our critical values, we're going to use that t-table that's in Appendix A, Table C. It's on page 884 in your textbook. It's also in the back of your course pack. With the row, so basically we're going to find where the row and column meet. So the row with n-1 degrees of freedom. So if you're doing a left-tailed test, you're going to use the area in one-tail column, but you're going to use a negative sign. So the t-table only gives you the positive values. So if you're doing a left-tailed test, you want the negative t value. So you just throw a negative in front of it, because keep in mind these distributions are symmetric. Similarly, for a right-tailed test, you're going to use the area in the one-tail column with a positive sign. And then for a two-tailed test, use area in two tails using both positive and negative. So let's look at an example. Let's find our critical value t0 for a left-tailed test given alpha equals 0.05, n equals 21. So we go to that t-table. So n equals 21 means our degree of freedom is 20. So we're going to go across this row. So we're going to be somewhere on this row. And then, in this case, since we're doing a left-tailed test, so area in one tail is left-tailed. And there's always a little picture here to help you. So you notice here, left-tailed test, area, and then there's your negative t. It's telling you use the negative value. So the table even helps you out with this. So in this case, area in one tail, we go across, we find our alpha level, in this case alpha equaling 0.05. So alpha equaling 0.05. Now be careful, make sure you go to the right column, don't go to 0.005. And we want to find out where that row and column intersect, and that is going to be our t value. So in this case, our critical value of t is going to be negative 1.725. So t0 is negative 1.725. Similarly, let's find our critical values for a two-tailed test, giving alpha is 0.1, n is equal to 26. So same idea. So alpha is 0.10, and we're in the two-tailed, so somewhere in this column. And n is 26. So that if n is 26, degree of freedom is 25. And so we find where they meet, 1.708. So in this case, negative t0 is negative 1.708, and positive t0 is positive 1.708. So to actually do the full t-test for the mean mu using critical values, so it's still going to be a statistical test for the population mean, and so it still has to meet the same requirements because we're still using the central limit theorem just in a different way. So you still have to have the population normally distributed or n greater than or equal to 30. T statistic, or the test statistic, is still going to be our sample mean x bar. Our standardized test statistic that we're going to use is t, and we calculate it using that same formula. So same formula we talked about in the last chapter. T is equal to x bar minus mu over s over square root of n. Looks very, very similar to our z-score formula. The only difference is we replaced sigma with s. That's the only difference. And then degree of freedom, or n minus 1. So we still do pretty much the exact same process. The only difference comes when we calculate the critical values using the t-table. So let's do an example all the way through. So a used car dealer says that the mean price of a 2-year-old sedan is at least $20,500. You suspect this claim is incorrect and find a random sample of 14 similar vehicles, which has a mean price of $19,850 and a standard deviation of $1,084. And we want to know, is there enough evidence to reject the dealer's claim at alpha equaling 0.05, assuming that our population is normally distributed. So population normally distributed, so we're good, meets the criteria for central limit theorem. So from here, our claim, so what we suspect then, we want to know, is there enough evidence to reject the dealer's claim? So the dealer is claiming mean price is at least $2,500. At least $2,500. So mean mu at least, remember, is greater than or equal to $20,500. That's our claim, or the dealer's claim. And because it has the equality, that's our null. The alternative then has to be less than 20,500. Means mu is less than 20,500. And we know alpha is 0.05. So figure out the type of test. Are we doing left-tailed, right-tailed, or two-tailed? In this case, since we know our alternative hypothesis points to the left, we're doing a left-tailed test. And one more step, since we know we're going to need it later. So degree of freedom is 13 because it's n minus 1. All right, so we know we're doing a left-tailed test. So t then is equal to, let's go ahead and calculate our test statistic. So t is x bar, which we found was 19,850, minus the assumed population mean of 20,500, divided by standard deviation 1,084 over square root of our sample size. Now be careful. It's over the square root of the sample size, not degree of freedom. So that's a common mistake I'll see students make, is they'll divide by the degree of freedom, but it's actually divided by the sample size. Remember, we use that degree of freedom to find our test statistic. And so we do this calculation, and we end up getting a test statistic. In this case, you want 3 decimal places, so negative 2.244. So now we need to find that critical value of t and figure out what our rejection region is. So we know we're doing a left-tailed test with degree of freedom 13. So left-tailed, so we're going to use a negative value. Degree of freedom is 13, so we're on this row. And our alpha value was 0.05, and it's a one-tailed test, so we use this top row. So then our critical value of t is negative 1.771. So we sketch out our region. So if this is our t distribution, and our critical value of t is negative 1.771, then everything to the left of that is our rejection region. Everything to the right of that is our do not reject region. So now we just compare our test statistic. So in this case, our test statistic, t is negative 2.244. So that is to the left of this. and so it lies in our do not reject, or in our rejection region. So in this case, we reject the null. So in this case, there is enough evidence to reject the dealer's claim that the mean price of a 2-year-old sedan is at least $20,500 at the alpha equaling 0.05 significance level. So don't forget to write that out in the context of the problem. So there is enough evidence at the 5% significance level to reject the dealer's claim that the mean price of a 2-year-old sedan is at least $20,500. So again, notice the similarities to doing it with the Z distribution. The difference just being that we're using S instead of sigma. Now it's worth mentioning, if we are going to do this with a p-value, the process for doing this with p-values is very similar to what we would do for z-values. So we would still go through, in this case we'd go to our degree of freedom, so which was still 13, but then we're going to look up our test value. So if we're on the degree of freedom row of 13, we want to look for our critical value, or our test value that we got, in this case negative 2.244. So in this case, so we know t is negative 2.244, and we know degree of freedom is 13. So we're going to look for that down here on this row. So negative 2.44. Remember, we can omit the sign when we're looking at the t-table itself. So 2.244. The problem's going to be it's not on this table. So all we can do when we're doing this for p-values is we can only find, okay, it's somewhere between 2.160 and 2.650 is our t-value. So 2.244. It's somewhere in between those two values. So that means all we can do is we can follow those two values up, and we were doing a one-tailed test. And we're going to get an interval for the p-values. The p-value is going to be somewhere between 0.01 and 0.025. So the p-value is somewhere in between those two values. So all we get, we don't actually get one p-value, we get an interval for the p-value. So the p-value is somewhere between those two values. So 0.01 and 0.250. So now the issue comes when we're comparing this entire p interval has to be less than or equal to alpha. And in this case, so both of these numbers, in this case, remember alpha was 0.05. In this case, this entire interval is less than or equal to 0.05. So, based on that, we have enough evidence to reject the null hypothesis. Now, the issue would come is one piece of this interval is larger than your alpha value. You automatically have to fail to reject. If one piece of the p interval is greater than alpha, you have to fail to reject the null. But in general, most of the time you're going to come to the same conclusion. And in this case we did. We came to the same conclusion. We reject the null hypothesis.